Whoa, I want to tell you about computers and I want to tell you about Albert Einstein, but before we do that, I want you to graph this function on your TI-84 Plus Silver Edition if you got one of these overpriced monstrosities. Check this out. I want the function to be y equals 1 over 1 minus x squared. This function right here, 1 over 1 minus x squared with the denominator in a scroot. Heck, you could put the scroot over the numerator also, I don't care. This function has a really beautiful graph, and I'll show you what it looks like. Let's see. Let's see. I set up my axes so that I've got 10 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I've got 1 here. So I'm going like this, and this is y, and this is x, and I zoomed in here, and it's like 1. It's like 1 for a long time, and then it just starts inching up a little bit, and suddenly it's like, boom! Not gonna go to 1, gonna go to infinity instead of ever reaching here. So this is a very interesting function. Notice how it's really flat over here, and then over here it gets really awesome. Okay, computers are very, very good at timing things. Computers can time incredibly well because they have crystals inside them, and they are able to measure the oscillation of the crystal. It's a little bit excited, and so you measure how long it takes for the crystal to shake back and forth, and you can measure time incredibly accurately. So a computer could make a clock that measures time based on the path of light. And it could say every time light comes from here to, well, let's say it's going from there and then hitting a mirror here, and then going back to here is one amount of time. We could call it a tick or something. And so this is a light clock. And well, the cool thing about light is it's moving at the speed of light during this time. So it'll be going at the speed of light on its way up, and it'll going at the speed of light on its way down. And this emitter here, the source of the light, has to be the same as the source of light has to be the same as the detector for the light. So that's the idea of a light clock. And I want to take these light clocks and I want to put 2 of them in our next problem. One light clock will be on a spaceship, and the other light clock will be on planet Earth, let's say. So here's planet Earth. It's kind of seafoam green, isn't it? There's planet Earth, and here is a nice person standing on planet Earth watching their light clock. They got themselves a fancy light clock, and the light clock, well, let's say it's on a little table so they can keep it horizontal. And their light clock is here, and they send light up, and it goes at the speed of light, and they send light down, and it goes at the speed of light, and they say that was a tick. Not going to claim that it's a second. Remember, this is our mirror right here, and this is our source and our detector. Source and detector in the same spot. So the light's going pew pew, and I just separated them from each other so that you can see one going up, and then that same light beam coming back down. That times for you. Inside of the spaceship, I'm going to make it a really big spaceship so that we can see the light clock, okay? Wow, look at that spaceship. It's like a bullet spaceship. Inside of the spaceship, there is another light clock, but the interesting thing about this guy is when he looks at the spaceship zooming by, see, the spaceship's going really fast. Here it is, going really fast. It's got a speedometer, and the speedometer just broke. The needle's like over here because it's going so fast. It would like to be somewhere over here in this healthy range right here. And it's going so fast that the speedometer broke. So, if this observer looks at the light clock that's in here, the observer will think, well, the light clock isn't at one place the whole time. In fact, the observer will say, you got those fancy light clocks just like I did, right? But the interesting thing is the light that's coming out of the source isn't going straight up because, well, I agree, at one moment the light clock will be right here. The next moment the light clock's going to be over here. And the interesting thing about it is, although someone's standing in here, there's somebody else really nice in here, and they are watching their own light clock, and they say, oh, it's just the same as your light clock, stupid, come on. It's going light up and then light back down. But this guy says, no, definitely. The light clock has moved from here to here during the time that it took for the light to get from there to there. So it's actually not going from here to here, it's going from here to the new position of the mirror. So the light, in fact, is going like this. Weird. Weird. Okay, then we'll have to think about the time and the distance that it's gone and all of this stuff. But that is, well, this time right here, we're going to call delta t. That's the time that it takes to go from there to there. And that time, well, should we get an equation for delta t? We might as well, right? That time that it takes is going to be 2 times the distance divided by the speed of light. And I'm going to say that distance is the separation between the two sides of the clock. So the time for one tick is from there to there. It's twice the distance divided by the speed at which the light goes. And I'm going to put a little subscript there, 0. That means this guy's looking at this clock and he doesn't see it moving. So he says the time is that big. When this guy looks at that clock, he's going to observe something completely different. We're going to still call this distance d. And we're going to say that during the time, oh, you want to define how fast this thing's moving? Oh, it's moving v fast. Now, don't be stupid. Of course, v is less than c, but it's not a lot less than c. It would not be fair to say v is much, much less than c, so I'm not going to do that. I'm just going to say it's a little bit less than c. If you want to put a number on it, you could say it's half the speed of light or something. I don't even care. So during the time that it takes for half a tick, that's just half a moment of time, the spaceship has gone a certain distance. How would we define the distance that the spaceship has gone? Well, I guess it's going to be the speed of the spaceship times the time that it took to go that far, which is delta t over 2. Isn't that distance right there? I think that it is. Now, I should probably use a different color for this. Sorry. Then a moment later, the light is going to hit the detector again. Now this guy, who's looking at his own light clock, thinks it's a stationary light clock, and he thinks the light's going straight up and straight down. But this guy knows better. He says, no, that light clock's going over to the right. So in fact, what you thought was light going straight up, you silly man over here, you've actually got light going at an angle so that it can hit your mirror. It hits your mirror and it bounces back down like that. And so there's a triangle in here as well. This triangle is a right triangle, and there's another right triangle, and we can put a dotted line right here and another dotted line right there, and we can do some interesting triangle stuff. So for instance, this distance here is d, that's one leg of the triangle, and this distance here is the speed of the spaceship times the time, which is half the time, because of course, like, this is also half the time. So if I were asked, what is this distance between here and here, somebody would come up to you and say, oh, that's just the speed of the spaceship times the time that it takes for a tick to happen. That's one action of the clock. So of course, half of it is going to be v times delta t over 2, and this is also v times delta t over 2. We can put that down there, v times delta t over 2. Okay, but what's this? Oh, light always moves at the speed of light. So this guy says that light is moving at the speed of light, which is weird because this guy also thinks the light's moving at the speed of light, but this guy thinks the light's going straight up because he's moving with the mirror. Does that make sense? He's moving with the mirror, so he thinks the light's going straight up and it's going to hit the mirror, which is still straight up. He's like leaning on the light clock. He's like, the light clock is not moving. But this guy says, no, stupid, your light clock is moving. Your light clock, light's coming out at an angle from your light clock so that it can hit the future light clock over here. And then that bounces off at a funny angle too, so that it can hit the future light clock, which is over there, because the light clock is zooming to the right at some really high speed. So fast you broke your speedometer. But this distance right here is one that we can solve as well. You see, light is always going at the speed of light. So this guy says that light is going, that's the distance that it goes is going to be the speed times the time that it takes, delta t over 2. Now we have a triangle. I'll make it blue for you. This is the triangle that particularly interests me at this time. It is a right triangle, and you know we can apply Pythagorean Theorem to right triangles, and the Pythagorean Theorem says a square plus b square is c square. A, that's just one leg of it. I don't know, want to call it d. Okay, that distance d right there, square. And then I've also got to square this one, which is v times delta t. Well, I better square that, and I better divide by 2 square. Okay, that's got to be equal to c square. C is this hypotenuse right here. That's going to be actually c square times delta t square divided by 2 square. Now we have ourselves a little bit of algebra to do. I want to solve this for delta t. Are you ready? Factor out a delta t, do a little bit of subtraction, d square equals delta t square times, what are we going to do some factoring? It's going to be c square over 2 square minus v square over 2 square. And then I can probably put the 2 square up top and, you know, basically just get myself a nice equation for delta t. It's going to have, well, I'm going to leave it as delta t square so we can do the final step on the next page. Delta t square is 2 square times d square over c square minus v square. And here's my plan. I've got a d square up top and a 2 square down here. Dang. What do you think I should do? Can I factor out another c? Yeah, let's write this again. I've got my, this is all just from the Pythagorean theorem on that triangle. Look at what Einstein's doing here. He says delta t is the square root of all this business right here. It's 2 squared times d square over c square minus v square. And we can simplify it just a tiny bit. First of all, we'll cancel out the stuff in the numerator. I get 2 times d, right? And then down here, I can factor out, oh, watch this. This is a little bit fancy. I'm going to factor out a c square. So I'm actually going to get a c down in the denominator here. And I'm going to say that this is 1, because I factored out a c square, minus v square over c square. And v square over c square is such a special number in special relativity. I'm going to define it to be beta, the Greek capital beta right there. And I'm going to plug in, is that capital? I think it might be lowercase. I don't even know. Look it up. So this then becomes, well, it's 2 times d over c times this funny thing. It's going to be 1 over 1 minus beta square, but the denominator is screwed. And I'm going to put that in parentheses and ask you if you've ever seen 2d over c before. 2d over c is the time that it takes for a click of this observer's clock. Click, clock. He's looking at this observer's clock and he says, no, sir, my light only has to go a distance d, but your light has to go a farther distance because it's not only going up d, it's also going over v times delta t over 2. So it's going a distance c delta t over 2. So when I have a second, your clock doesn't even complete a second. He says, your clock's running slow, sucker. He thinks his clock is running slow, and he's correct. Because we find that the time, this delta t, is the time that my stationary observer says it takes this clock's to make a tick. Let's see what it looks like. Delta t is going to be delta t naught. That's this right here. Look, it's right here. That's delta t naught. That's the time that this observer says is an actual tick. And then he says it's that stuff times 1 over 1 minus beta square over 2. You've studied this relationship right here. This is something that I'm going to define to be gamma. Gamma is 1 over 1 minus beta square over 2. Rather than nesting my definitions, I'll put it all full blown out here. Gamma is 1 over the square root of 1 minus v square over c square. Okay, so that's gamma, and gamma has this really funny property. Let's first study beta. Beta's got to be less than something, right? Beta, it seems like beta always has to be less than 1, because you are not going to succeed if you're trying to get faster than the speed of light. That's fine. So if beta is less than 1, and I'm scoring it, I'm going to get even smaller. Every time you score a number less than 1, it gets smaller than it was before. So I'm going to take 1 minus a number less than 1. In fact, sometimes that number is very, very small. In fact, well, let's just try it out. Let's try out what gamma is going to give us. I'm going to give us gamma for beta equals 1/10. Let's try that. Gamma, when beta is equal to 1/10, check this. I'm going to do 1 divided by the square root of 1 minus 0.1 square. Ready? Oh my goodness, it's just 1.005. Wow. So if I am looking at how things change, how time changes, If you're going 1/10 the speed of light, I guess if beta, wait a second, I need a new color here, sorry. If beta is V over C, if I'm going 1/10 the speed of light, then I could say that my speed is 0.1 times c divided by c. That just gives a beta of 0.1. So beta is a really nice thing. It helps you get c out of your equations. So I'm plugging in beta is 1/10, and I find that there's only a 0.5% change. Dang, only a 0.5% change in the amount of time that these people observe, because this is, wait a second, this says the time that the stationary observer sees is his own time multiplied by gamma. And gamma, let's see, what are the range of gamma? How can gamma range? I guess the lowest that can, wait, we were working through this, right? We said that beta is always less than 1, and if I'm taking 1 minus the number less than 1, then that's going to be in between 0 and 1. And then I screwed that. Oh my goodness, if I screwed it, it's actually gonna get a little bigger because it's between 0 and 1. And now I have a number that is between 0 and 1, and I'm dividing 1 by that number between 0 and 1. Are you ready to do that? This gamma, therefore, is going to be bigger than 1 all the time. The only time gamma could be 1, let's try it out. If beta equals 0, then if beta is 0, then we're taking 1 minus 0 and screwing it, we get 1, so gamma is 1. What if beta is really big? Well, we can look at that at another time. But if beta is really big, let's say it's almost 1, then this is an extremely small number in the denominator. We screwed it, and we still get an extremely small number. So we'll have 1 divided by an extremely small number. I guess gamma can be really big. It just has to stay smaller than infinity. Could it be equal to infinity? Well, maybe. I guess if beta were actually 1, then we would have infinity over here. Yeah, so I guess that's if things are moving at the speed of light. The speed of light has an infinite gamma. Yeah, I said it. Deal with it. So here's what we've got. We have proven that this guy says this guy's clock is moving more slowly, and he's correct. But we said yesterday that every single physical process is the same for every observer in an inertial reference frame. So it's not just this funky light clock, it's like when this observer looks at this guy on the rocket ship, he thinks he's moving slowly. He thinks that his machines are processing slowly. This observer thinks that that man is thinking slowly. In fact, he also thinks that he's living slowly. He thinks his heart is beating slower, and he thinks he's going to die later. And he's right. This person sees that guy doing everything slower because time itself is slower for this guy. Time is slower for him, but oh boy, Albert Einstein comes in and he says everything is relative. The guy who's on this spaceship looks down at Earth and says, Earth, that's funny. I'm still on my spaceship, but Earth is zooming by that direction. And that clock that you think is just going straight up and straight down is actually sending light beams at a funny direction. It's like, pew, 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 pew. Not straight up and down, but in fact, the light has to go farther. So this guy says this guy's clock is going more slowly, and he's right. So let's summarize. This guy says that guy's time is going more slowly. This guy says that guy's time is going more slowly, and they are both correct. Deal with it. Special relativity, suckers.